So today we have Bridget Schreiner talking about stability in the homology of configuration spaces.
Great. Hi, everyone. Thank you for coming, and thanks to Sarah for organizing this and giving me the opportunity to speak. Of course, in keeping with the theme of the seminar, I needed a picture of GROOT to go on the first slide. And in looking for this picture, I stumbled across the often Googled question, what does I am GROOT mean? And Google informed me that I am GROOT means you are boring. So if I see that in the chat, I'll know what's going on. So in this talk, I'm going to start out by giving an introduction and introduce the example that we'll be looking at throughout, which is going to be the homology of configurations of ordered points in R2. I'll give a really brief introduction to representation stability and kind of just the idea of what that means, and then introduce a model for the homology of configuration spaces that we'll use to then see the secondary or the representation stability and hopefully the secondary and higher stability, although that's going to be dependent on time. Just as a brief introduction to why I'm working on this project, I work with Mark Behrens, who does not usually do representation stability, but I became interested in questions about homological and representation stability a couple of years ago, and Mark had seen some things that he thought indicated that calculus of functors might be involved in these questions. I also have a strong interest in calculus of functors, so kind of the eventual goal of this project is to work towards connections between stability and calculus. The stage that you're seeing right now is just us looking at kind of a toy example, which is the configurations in R2, so that hopefully we know what's going on. We can then use that to look at connections. So to start off, we're going to take a connected, non-compact manifold without boundary of dimension greater than or equal to 2. Throughout this talk, R2 will be what we're thinking about for the most part, but it's easier to draw pictures with the punctured torus I have here. So this is the picture that we should have in mind for now. We define configurations of n points in M to be the set of n tuples of points that are all pairwise distinct. And these are ordered configurations, so they have labels from the set 1 through n. And note that we have an action of the symmetric group on this space just by permuting the labels of the points. Because M is non-compact, we can pick an embedding of M union RD to M, which is nice enough, which basically means that we can insert a copy of Euclidean space kind of out near infinity is how you can think about that. And nice enough just means that it's isotopic to the identity. So it's not changing the manifold too much by inserting this copy. And this gives us the ability to get a map from configurations of n points to configurations of n+1 points. Note that we always have a map going the other way just by forgetting one of the points, but we need the non-compactness of M to get the map going in this direction. And this we do by just taking a configuration in M to its image under the embedding, and then adding an n+1st point in the image of RD. So basically what that embedding we have is doing is it's distinguishing a place where we can add a point that's separate from the points we already have in the configuration. If we didn't have that, then there wouldn't be a well-defined way to add a new point and get a configuration of n+1 points. This induces a map on homology. Note that the original map isn't necessarily well-defined except up to homotopy, but we do get a well-defined map on homology. If we're interested in homological stability, then we ask whether this is an isomorphism once n gets large enough relative to the homological degree. Unfortunately, this turns out to not be the case, as we'll probably see later in the talk. I should mention that if we're looking at unordered configurations, we do eventually get an isomorphism on homology groups. But with ordered configurations, we have that action of the symmetric group, and that we'll see later forces each group, the n+1st group, to be somehow bigger than the nth group. So this fails homological stability, but if we look at the sequence of fixed degrees, so hi of conf n, we can ask whether this stabilizes in some other way. And the answer for that turns out to be yes, which is why we think about representation stability. So in the traditional setup for representation stability, we start with a sequence of vector spaces, v1 to v2 to v3, etc. And Vn has an action of sigma n, the nth symmetric group. We ask that these maps, phi n from Vn to Vn plus 1, be sigma n equivariant, where we just think of sigma n acting on both sides by including it into sigma n plus 1 via the standard inclusion. And the idea of representation stability is that the sequence is representation stable if the n plus first vector space is generated by, and I'm being a little vague by what I mean by generated by, but it's generated by the image under phi n of the nth vector space and the action of sigma n plus 1 for n large enough. This idea was originally due to Church, Ellenberg, and Farb, and the original definition is a little bit unwieldy, so I'm not going to give the specific definition here. So a completely natural question is, does this condition mean that the n plus first vector space is the induced representation of sigma n up to sigma n plus 1 of Vn? And this turns out to not be the case. The induced representation is a bit too big, but there is a condition defined by Andy Putman that gives us representation stability. So a condition that implies representation stability is that Vn plus 1 is the largest quotient of the induced representation, such that the transposition n plus 1 fixes the image of Vn minus 1. And we require that because of basically just the equivariance of the map. Maps tells us that the image of Vn minus 1 has to be fixed in Vn plus 1 by this transposition. And so it turns out that if you kill off everything that doesn't fix that, then it's fine. And we actually have representation stability. This condition is called central stability, and I think is sometimes equivalent, but it does always imply it. So for example, we have our sequence from the beginning. So for a fixed homological index I, we have hi of conf 1 to hi of conf 2, etc. And each time we have an action of the symmetric group just induced by permuting the points in the configurations. And there's a theorem due to Church, Ellenberg, and Farb that this sequence is representation stable when n gets to be bigger than or equal to 2i plus 1. So once we get configurations of 2i plus 1 or more points, hi of configurations of n points is generated by the image of the other homology groups and then that action of sigma 2i plus 1. Are there any questions so far?
Yeah, I actually have one. Which coefficients are you considering your homology in?
Integer.
So, okay.
Yeah. Okay, so the next thing I wanted to talk about is the model of homology of configurations in R2 that I'm using. I got this from a paper by Dev Sinha, although the idea was originally due to Fred Cohen and has been changed a fair amount over the years. But the presentation that I'm looking at, I got from Dev Sinha. So we're going to describe classes in the ith homology by maps from an I torus to configurations of endpoints in R2. And this gives us an element of homology just by applying homology to that map and taking the image of the fundamental class. And these maps are going to correspond to trees where each tree or the forest has a total of I total internal trivalent vertices. I'll give a picture of what this looks like in a second. Each tree has one distinguished univalent vertex, which we'll call the root. And then all of the other non-root leaves have labels from the set 1 through n. We don't need to have all of the numbers 1 through n appearing as labels, but each number appears at most once, and they're all from that set. So for example, here is such a forest. We have 2 trees. The first one has 2 internal trivalent vertices, and the second one has 1. So this is going to be an element in the third homology. And then we have labels 1, 4, 2, 6, and 3. So labels from the set 1 through 6 or 1 through higher. And we want to get a map of a torus from this. So the way this gives us a map is if we look at the first tree going up from the root vertex, that first splitting in the tree tells us that there's a point with a label 2, kind of orbiting the origin with points labeled 1 and 4 on the other side. And then the second splitting there into 1 and 4 tells us that those 2 points are orbiting the point antipodal from x2 on that circle around the origin. And then the second tree is telling us that 3 and 6 are orbiting. Usually we just pick the point 1 on the x-axis. These diagrams are called planetary systems. So it's always fun to read a sentence that's something along the lines of, we describe homology classes by forests of planetary systems, because that's a lot of seemingly non-math words. But these are how we describe homology classes. So this one is going to be a class in the third homology of configurations of 6 points. And notice that because 5 isn't a label on the tree, there's just a point labeled 5, x5, fixed out away from all of these. It's usually described as being kind of out near infinity, but you can think about it as living in that neighborhood that we inserted in the map that I originally defined. Just basically picked so that it's far enough away from the other points that it's not going to collide. More precisely, if we want to write this map down, if we have a tree with I internal vertices, and then you just repeat this if you have a forest, we fix an epsilon greater than 0. I think usually it's picked to be 1/3, but it doesn't really matter. And define the map where we have one circle for each internal vertex. So S1 crossed with I to conf n or 2 by taking a point in the torus uv1 up through uvi, where the coordinates are indexed by the internal vertex that they correspond to a configuration x1 through xn, with the kth point in that, we define it to be the sum over all of the internal vertices below that leaf of plus or minus epsilon to the height of the internal vertex times the coordinate of the point on the circle corresponding to that internal vertex. And that sign, the plus or minus, just depends on whether the leaf with the label K is above the left or the right edge out of the internal vertex. And then, like I said, HJ is the height of VJ. So it's not super important that you understand what this map is doing. Basically, it's just taking the coordinates corresponding to an internal vertex and constructing a point in the configuration out of that. The epsilon is what controls the radii of those circles that I had in the previous slide. And then the plus or minus is what makes those points antipodal on the circles from each other. But the basic idea here is just that we have these maps from tori to the configuration spaces, and we can classify them just by drawing these types of forests.
Can I ask a question about configuration? So can I consider configuration, the sequence of configuration spaces when n varies as an operand and say that homology is some kind of also an operand? But I cannot say, like, I'm not sure because because you consider the integer coefficients, and you have to be careful about how maps going. And when I just think this is a composition with operand for configuration spaces, indexed like trees.
Yeah, so you have to be a little bit, I'm sweeping a couple details under the rug here. So you have to be a little bit careful about the orientation because we're using integer coefficients. So we just wind up picking, I think it's the outward orientation and then using the product. So on each circle, we pick an outward orientation and then define the orientation on the torus to be via the product. And then I think it winds up being some kind of Poisson operad, but I don't remember exactly.
No, orientation is just you have to identify configuration space of 2 points with a circle. I think this is a choice of configuration here.
But yeah, so it does wind up being an operad. I'm not too concerned about that structure. I really just want to be able to count all of the homology classes by counting the number of forests that look like this.
Yeah, okay, yeah, sure. I'm just,
yeah.
I mean, it looks like an operad in some trees.
Yeah.
It appears, so I have to say.
Yeah, no problem.
Okay, no problem.
Are there any other questions? Okay. So it turns out that a basis for the ith homology, we don't have to consider all of the possible things. This structure with the forest winds up having an anti-symmetry and a Jacobi identity, and I think some kind of anti-commutativity. So we only wind up needing to consider forests of trees of the form that I've drawn below. So basically at each internal vertex, there is a branch off to the right and then nothing after that. And then for the labels can be in any order after the first label on the left, but the first label on the left needs to be the least element of 1 through n appearing as a label. And then if you have multiple trees in a forest, the trees need to be ordered by those leftmost elements. All right, so a quick kitten break following Nico's example. Hopefully no one has reached this point yet, but if you have, I want to give you a second to wake yourself up and also just pause for any questions.
So is it the forest as a whole that's forming a basis, or are like each element individually in the forest what matters?
So a basis for the ith homology is the set of possible forests with I total internal vertices, and then labels of the form on the previous slide.
Thank you.
Yeah. Okay, so the goal for the next part is to be able to see the stability happening for configurations of points in R2. So we had this sequence from earlier where we have the symmetric groups acting on the homologies. And we want to show that once n is greater than or equal to 2i plus 1, the map from the ith homology of configurations of n minus 1 points to the ith homology of configurations of n points, together with the action of sigma n on that, completely generate the ith homology of configurations of n points. So we can now see what this map is doing on homology in addition to on the configuration spaces. Specifically, it's just taking a forest in hi of configurations of n minus 1 points, basically to itself, and then adding a point xn at infinity, if we think about that picture with the planetary system. So for example, if we look at the second homology of configurations of 3 points, we have this tree with just 2 internal vertices and labels 1, 3, and 2. And in this map, that just gets taken to itself. So it looks like it doesn't change anything at this level. But what's really happening if we look at the picture in R2 is just that point x4 is getting added far away from the other points in the configuration. So we can now see what the image of this map is. It's going to wind up being all forests of tree shapes that occur in hi of conf n, that don't have n as a label because we don't have that in hi of n-1. And I'll draw a picture to make this a little bit more precise in a minute. But basically, if we look at the tree on the right, it has the same shape as the tree on the left. But in H2 of configurations of 4 points, we have trees that look like that, but that have 4 as one of the labels. And those are not going to be in the image of this map, just because the labels remain unchanged under the map. But once we add in the action of sigma n, this permutes the labels of the trees, and we then start to get the forests that have n as a label on one of the trees. So we will get trees that look like this homology class, but have, say, 1, 3, 4, once we start adding in that action of sigma 4. And so when thinking about stability, we only need to think about the shapes of these trees. We don't need to consider the labels, because the action of sigma n will create the trees with whatever labels we need. So for example, if we look back at this homology, second homology of configurations of 3 points, the only possible forests here are the one tree with 2 internal vertices, because we only have 3 labels to choose from. So the other possible forest with 2 internal vertices is shown on the right there, and it has 2 trees, but in order to put labels on all of the leaves there, we need at least 4 labels. So that class does not appear in the second homology of configurations of 3 points, just because we don't have enough labels to be able to put on all of the leaves. So just to make that a little more precise, we have the blue tree in the image. Anything that looks like that is in the image of this map, and the action of sigma 4, because we need to get that label of 4 on the leaves. But the one on the right is not in the image, and so we do not have stability at n equals 4 yet, because we have this new class appearing. So the question then becomes, can we see where the stability happens? So I started writing out examples, basically. So if we start with I equals 1, there is only one possible forest with 1 internal vertex. We get this. And the number of labels we need is n equals 2. So the first n where we see that class appearing is in H1 of configurations of 2 points. And that's the last new class. After that, every homology group will have that class with various labels, but we don't get anything else in H1. If we look at I equals 2, this is the situation we had before, where we have either just one tree with 2 internal vertices, or we have 2 trees each with 1. And the first one appears first when n equals 3. The second one appears when n equals 4. And then after that, any homology group will have these 2 classes with different labels, but no new classes appearing. If we go to 3, we start out with just one tree with 3 internal vertices, starting in n equals 4. We have another forest that requires 5 labels with 2 trees, and then another that requires 6 labels with 3 trees, each with 1 internal vertex. And that pattern continues in that the last new class to appear is going to be this class of I trees, each with 1 internal vertex. And we can see that that appears first in configurations of 2 I points, because we need 2 times I labels in order to label all the leaves on those trees. And so after that, we have no new classes appearing. So if you look at HI of configurations of 2I plus 1 points, we just get all of the classes from lower homology groups, and then the action of sigma 2I plus 1 generates all of the things we need in terms of different labels. And if we recall what we're trying to show, we were trying to show that the sequence becomes representation stable at n equals 2I plus 1, or it's stable for n greater than or equal to 2I plus 1. And if we look at R2, we can see that that happens simply because the last new class to appear requires 2I labels. And then after that, we always have enough labels for all the possible classes, and we get stability. So yay, that's what we were trying to show. Are there any questions on this section?
So does representation stability happen when there are no new shapes that occur?
Yeah, in this model, yes.
Awesome.
Yeah.
I have a question.
Yeah.
What about like trees with more than 3 for valence?
So one of the rules for the trees in these is that the internal vertices have to be trivalent.
So
Yeah,
this is kind of like the way you're designing these circles is to sort of have like them all at individual points so they don't like interact with each other.
Yeah, exactly.
Interesting.
So one thing that was kind of surprising here was that the original theorem was for a general manifold M. And we weren't really expecting the bound for R2 to be the same as for a general manifold M, but it wound up working out that way. So we were a little surprised by that, but we're hoping that that will help with the next stage of our project, which is where we're going to be looking at secondary stability and potentially higher versions of stability. So one way to think about the question of secondary stability is we know the sequence stabilizes starting at 2i plus 1, but before that happens, we wanted to ask if there was some other kind of stability happening. So if the sequence is changing, but those changes are constant through some range. And Jeremy Miller and Jenny Wilson defined a way to think about this that they called secondary stability. So we were working with that. So if we recall, we have this map from configurations of n-1 points to configurations of n points. And that's just induced by adding this nth point far away from the first n-1 points. And in particular, we had that embedding from n union R2 to m. We also, it turns out, get a map from configurations of n-2 points to in m across configurations of 2 points in RD, which here I'm just using R2, to configurations of n points in m, just by placing 2 points in the image of R2. And that's an element of the configurations of 2 points just because they have to be distinct. By applying homology, we then get a map from the 8th homology of configurations of n-2 points in M, tensored with the bth homology of configurations of 2 points in RD, to the a plus bth homology of configurations of n points in M. And we can use this to give us a map from the I-1st homology of configurations of n-2 points in M to the ith homology of configurations of n points in M, just by picking a class in H1 of configurations of 2 points in RD. So here we're going to pair a class in Hi-1 of configurations of n-2 points in M, with the class of just 2 points and n-1 orbiting each other in H1 of configurations of RD. This map is only interesting if D equals 2, because we have this circle, and so it would be null homologous if we had D is greater than or equal to 2, but we're only interested in manifolds of dimension 2 here, so that's okay. If we look at our model for the homology of configurations of endpoints, this corresponds to taking a forest and just putting the tree that looks like a Y with n-1 and n at the end. That raises the homological degree by 1 because we're raising the total number of internal vertices by 1, and then it raises the number of points by 2 just because we're adding the labels n-1 and n. So we're now looking at the 2 maps into the ith homology of configurations of endpoints. And Jeremy Miller and Jenny Wilson showed that the ith homology of configurations of endpoints is generated by the images of the map we were looking at before. and then this new map that we defined from the I minus first homology, and then the action of sigma n. And in their paper, they weren't yet able to give ranges for the values of n for which this worked. So one of the goals that Mark and I had in looking at this example in R2 was to use a simple example to be able to calculate some ranges here. If we go back to our model for the ith homology and look at each of these forests, we can see that a forest with I internal vertices corresponds to a partition of I into k pieces, and a partition of I into k pieces requires I plus k labels, where these elements aj are the number of internal vertices of the trees in the forest. So to put partitions to these, this first one is just the only partition of the number 1, so we just get 1. For I equals 2, we have 2 partitions of the number 2, we have 2, and then 1 plus 1. And for I equals 3, we just have the first one, which is 3, 2 plus 1, and 1 plus 1 plus 1. So each of these forests just corresponds to one of these partitions. And this just gives us a shorthand for being able to write out exactly what this means, because when I gets really big, drawing these trees gets very annoying. So this gives us just a shorthand for being able to record what these forests look like as I gets larger. So just to reiterate that, classes in the ith homology of configurations of endpoints correspond to partitions of I into n minus I parts. I should say new classes in homology of configurations of endpoints in R2 correspond to these partitions because a partition of I into n minus I parts requires exactly n labels. So if it were fewer than that, it would have appeared in a lower number of, we would have needed fewer points. So it would have already appeared in one of the homology classes. If we recall, we defined this map from the I minus first homology of configurations of n minus 2 points to configurations of endpoints by just adding this tree with one internal vertex. And if we look at our rule of what the partitions mean, the numbers in the partition are the number of internal vertices. And so this map corresponds to taking a partition of I minus 1 and just adding a plus 1 to it to get a partition of I into the appropriate number of parts. And so when we're thinking about what secondary stability looks like, we want to know for which n we have all possible new classes being generated by these two maps. And the claim is that this corresponds to taking any partition of I into n minus I parts, at least one of those numbers has to be 1. So if we're looking at secondary stability, we're looking for all new classes to have either already appeared or for them to have come from a partition of I minus 1 by just adding 1. Sorry. So to give an idea for why that's true, we just need to know basically what I said, which is why those classes have already occurred, or if they come from taking a class in a lower homological degree and adding 1. So if every partition has a 1 in it, that means that it comes from a partition of a smaller number and adding 1 to get a new partition of I. So now the question of secondary stability for us in this model looks like just asking for which values of k will any partition of I into k parts contain a 1, which turns out to be an easier question to answer. So if you just take floor, for example, floor of I over 2 plus 1, then if we have a partition of a number into that many pieces where each piece is greater than or equal to 2, then the number we've partitioned has to be greater than or equal to 2 times the number of pieces, which is greater than I, just because the pieces, or there are at least I over 2 plus 1 pieces. So this is no longer a partition of I. And that tells us that for the values that we're looking for, we need the number of pieces in the partition to be greater than or equal to I over 2 plus 1 in order for this partition to have a 1 in it. And that tells us that the number of points we need, or the n, is going to be greater than or equal to I plus floor I over 2 plus 1. And that gives us a range for secondary stability, because all we needed to know was when all of the partitions have a plus 1 in them. When I originally did this, I wasn't thinking about it quite in terms of how many pieces do I need to get a 1 in the partition. I was basically just looking at experimental data and finding patterns in that. So the original way that I wrote this was n greater than or equal to 2i minus floor of I minus 1 over 2, just because that fit the patterns I was seeing. It turns out that these are the same. And I prefer to write it as the n greater than or equal to 2i minus the floor of I minus 1 over 2, just to make the comparison with the representation stability range more clear. And I'll hopefully get to showing a chart that shows that comparison more clearly later. Are there any questions on this part?
Can you just remind me of the definition of secondary stability again?
Yeah, sure. So so secondary stability, let's see, I'll go back to it. Sorry, hope that wasn't making anyone dizzy. So secondary stability means that we're generated by the image of the map from the ith homology of configurations of n-1 points, as well as the map from homology, or the I-1st homology of configurations of n-2 points. That first map is by just adding a point out near infinity, and the second map is by taking a forest and adding the tree with 1 internal vertex to the end of it. And then we also have the action of sigma n to permute the labels of the trees.
Okay, just wanted to be sure I was comparing it to just stability, correct?
Yeah, it's hard with slide talks when you can't just like look up at the board that was earlier. And then the last thing I wanted to talk about was an idea for the generalization to k-area stability. I should say a little bit of a disclaimer here, which is that I've been sweeping some of the details under the rug in terms of secondary stability. The way that that was defined followed the categorical framework of FI modules and required some pretty heavy-duty algebra in order to technically define in the case that Jeremy and Jenny were working in. As far as I know, that algebraic and categorical framework does not yet exist for things like tertiary stability or four-area stability. So this is basically an idea of what Mark and I think it should mean, but we don't yet have the algebraic structure to make it really precise. But if we go back to what we were thinking about with secondary stability, we were looking at the inclusion of the ith homology of n-1 points, and then the map from the I-1st homology of n-2 points. And this corresponded to all partitions of I into n-I parts, ending in a +1 when ordered non-increasingly, which just makes it easier to see whether or not there is a 1 in the partition, is if we just order it non-increasingly and look at the last number, see if that's a 1. So we think that tertiary stability should involve the two maps that we already have, and then a map from the I-2nd homology of configurations of n-3 points to the ith homology of configurations of n points, just by adding this tree with 2 internal vertices to a forest. And similarly to the secondary stability, this should correspond to all partitions of I into n minus I parts, ending in either a +1 or a +2. So that would tell us that new classes in HI of configurations of endpoints come from either 1 degree lower by adding a 1 or 2 degrees lower by adding a 2. And then to bump this up to K-area stability for a general K, we should look at the collection of maps from H I minus j plus 1 of configurations of n minus j points, where j ranges from 1 through k. And these maps should each be just by adding the tree with k minus 1 internal vertices to the original forest, and then permuting the points. And similarly to the other case, this should correspond to when all partitions of I into n minus I parts end in +1, +2, or up through +k minus 1 when ordered non-increasingly. So we started looking at this, and the claim is that the sequence of the ith homology of configurations of endpoints should hopefully satisfy what we're calling K-area stability when n gets greater than or equal to 2i minus floor I minus 1 over k. So it should look like the range for secondary stability, but with that 2 in the denominator replaced by a k. And that should just be basically the proof that I had for why partitions of I into that many pieces have to contain a 1. It should follow a similar line that partitions of I into floor I over k plus 1 pieces have to contain a 1 up through k minus 1. And then I put this note that I needs to be sufficiently large here, which I'll show a picture for what I mean by that in a minute. This didn't come necessarily from anything theoretical, it just came from what we noticed when we were looking at the data.
Sorry, so this claim says that the more refined stability happens in smaller range.
Sorry, what do you mean by smaller range?
You say that n greater or equal to I minus some I minus 1 over k. So if k is large enough, then this n also should be large. It should be bigger. This bound should be bigger than bound for small k.
Well, so we're subtracting off the I minus 1 over k. So as k gets larger, we're subtracting off less each time.
So I fixed I, but I changed k.
Right.
So when with low bounds will be bigger.
Oh, yeah. I might have made a typo here. Sorry about that.
But this is expected behavior or not?
Yeah, so as k grows, K-area stability should happen for smaller and smaller values of n, because we're looking at, so the stable range.
Image is bigger.
Yeah, so yeah, a sign might have gone missing somewhere. I'm not entirely sure about that right now, but I'll show you the chart in a second that shows kind of how the slope is changing.
Okay, great.
Yeah.
Sorry, can I ask you a quick question?
Yeah, sure.
So is this what you imagine your condition for like k excisive would be, connecting it back to the functor calculus?
Not quite. So we were thinking of it more as, if you think about in regular calculus, the cross effect of a function is measuring the differences in higher and higher ways. So if you look at the difference between values in, say, a sequence, maybe when we're asking for a sequence to stabilize, the differences should be getting closer and closer to 0. But maybe they don't get closer and closer to 0, they just get closer and closer to, say, 2. That should correspond to something like the second cross effect of a function, which should correspond to what we're looking at as secondary stability. So the cross effects measure how far something is from being stable, and we're thinking that these k-area stability ranges should correspond to the kth cross effects of some functor.
Okay, thanks.
Yeah. So to look at kind of where the patterns were happening, I basically spent a week color coding this spreadsheet. So this was my life for a while. I found some Python code that allowed me to put in which number I wanted partitions of and how many parts I wanted that partitioned into. And then I color coded the box based on what all of the partitions ended in. So if you look at this green area, this is where the primary stability is happening. And you can see that 2i plus 1 happening if you just look at the bottom edge of that range. We have that pattern of kind of down 1 over 2, down 1 over 2, etc. And then the blue range was this secondary stability range. So if we look at this, we can see a pattern emerging of kind of going, here, I should probably draw this, down 1 over 1, down 1 over 2, down 1 over 1, down 1 over 2. And that's that we have a slope of 2i that's changing, and it changes every 2, just because we have that floor function of the I minus 1 over 2. And we can see that happening with the other colors too. So the blue is what we're calling tertiary stability, and we see that down 1 over 1, down 1 over 1, down 1 over 2 pattern. In general, for the k-area stability, we have a down 1 over 1, down 1 over 1 pattern that happens for k minus 1 places, and then that switches to going down 1 and over 2. So basically, it resets every k, which is why we had that I minus 1 over k in our range, which there might have been a sign in that. But basically, we should get a shift in how that's behaving every time I goes up by k. And that's what's causing these ranges to not be completely linear all throughout. We can see that the blue range is getting wider as we go down, and so is the purple range. If I had been able to include more of this chart, you would see the same with all of the other ranges. They're widening as they go down. And so they're not changing in completely constant ways, which was a signal to us that there's something calculus related going on here, and it's not quite so simple. So I think I had 50 minutes, and that was about all I wanted to say. So thank you, and are there any questions?
Thanks, Bridget. I'll unmute everyone so we can thank Bridget. And then questions for the recorded question.
So probably I have to ask like another question here. So your definition of time stability works only for sequence of symmetric group and only for one space, which is looks like homology of one space, which looks like a. Do you have some ideas how to generalize it?
Sorry, the beginning of your question got cut off.
So your definition of high stability is only for sequence of symmetric groups, so only symmetric group size, and only in your definition you're using what this is a homology of configuration spaces. So do you have some ideas how to generalize it in more general context?
So the main ways in which we want to generalize this are just two general manifolds other than R2, and also dimensions higher than 2. We haven't thought about other groups. In terms of other manifolds, it should be essentially what we have here, which is appending a class in the image of R2 under that embedding with just points orbiting each other.
But you have ideas how to do it in high dimensions too.
Yeah, so instead of maps from a circle, we were just thinking about it as maps from a higher sphere. So it would be maps from a higher dimensional torus, and that way the maps aren't completely killed by the higher dimension of the space.
Sure. Yeah, nice. Cool.
Any other questions for Bridget? All right, I'll go ahead and stop the recording here.
I actually have a question. Sorry.
Continue.
So does your calculation give anything new about the unordered configurations? So if you quotient out the action by the symmetric groups, you get the classifying spaces for break groups. And there you have like actually homological stability, but you could also ask what is the homology outside the stable range? Could you apply calculations to say something new there?
I think so. There is a notion of higher homological stability, but I've only seen that for mapping class groups. So I have thought about applying this to higher homological stability for unordered configuration spaces, but I haven't seen anything with that yet.
Sorry, I also have another question, but this is a little bit vague. So suppose I have these spaces and so I choose some I and I have an action of a group on each space itself. And I know that I have a representation stability for homologies as a representation of these symmetric groups. But now, can I say that I have some usual stability when I take a quotient of these spaces by group action and take homologies?
Sorry, the first part of your question cut out from my audio. What was it?
Sorry. Yeah. So just second is the following: you have sequence of spaces, and each spaces has this action of symmetric group, for example, and you take HI, homology groups, and you get a representation stability, or some variant which you like most. But can I say something about stability of homologies of quotient of the spaces by group actions?
I believe so, but I don't know off the top of my head. I have seen proofs of representation stability used to give better ranges for homological stability. So you should be able to do something like that.
Okay, yeah, good.
Any other questions for Bridget? Okay, I'll go ahead and stop the recording and then we can thank Bridget one more time.